Hi everyone. Thanks for listening to my talk. I'm Subhajit Das, PhD student from Georgia Tech. I will be talking about our paper, Gaggle, Visual Analytics for Model Space Navigation. Recent visual analytics systems make use of machine learning models to support user tasks. These systems are traditionally built by a predefined model, also called single model systems. For example, interaxis that allows users to interactively change an axis, or dysfunction that allows interpreting a similarity function based on user interaction. When a model is correctly chosen for the phenomena, task, or data distribution, such systems can effectively support users in exploration and analysis. However, in cases where the right model to use for a problem is not known, one needs to find a fitting model for the task or the problem. These are shown by the recent systems that rely on multiple machine learning models, such as cluster vision or beams, supporting interactive clustering and regression tasks, respectively. Multi-models are useful as they help users to choose an optimal model suited to their problem domain. They also help users to understand the data in light of different model parameterizations. However, while multi-model systems can be effective, their added complexity adds usability concerns as users are required to interact with the parameters of multiple models. Further, the advent of various model algorithms poses the complexity to navigate an exhaustive model space to find the right model for the data and the task. In this paper, we present Gaggle, a visual analytic tool that provides the user experience of a single model system, yet leverages multiple models to support the data exploration. Gaggle constructs multiple classification and ranking models, and then using a Bayesian optimization-based hyperparameter selection technique, automatically finds a classification and ranking model for users to inspect, thus simplifying the search for a user-preferred model. In other words, Gaggle facilitates interactive navigation of the model space. Gaggle uses machine learning to help users in data exploration tasks, such as grouping and ranking data in self-defined categories. For example, a professor may want to use Gaggle to help categorize and rank new student applications in different sets to decide on whom to accept or reject. Similarly, a baseball sports coach may wish to categorize and rank players in different groups based on their performance in the playoffs. Classifiers constructed using Gaggle are not meant to predict labels for unseen data items in future. In other words, Gaggle only uses training data for data exploration, does not export models to predict labels for test data. Furthermore, Gaggle addresses a common problem of datasets that either lack adequate ground truth or do not have it. To resolve this problem, Gaggle allows users to iteratively define classes and add labels. Gaggle supports the use case of allowing data exploration and model construction simultaneously. This is challenging because in the course of data exploration, a user may change their task definition or learn new information about the data. In these cases, a user feedback may be better modeled by a different model hyperparameterization compared to earlier in the task. For example, in an earlier iteration, a linear decision boundary might characterize the data. However, when new examples for classes are provided, the decision boundary might be better approximated using a polynomial or radial surface. In situations like this, Gaggle helps users by navigating the model space to find an optimal model without users having to learn model parameterizations or model metrics. Next, we define a set of terminologies that are relevant to the topic of discussion. We define models as a careful combination of a chosen learning algorithm and a set of hyperparameters such as shown here. Varying the learning algorithm and the hyperparameters creates a diverse set of new models. The space of every possible combination of learning algorithms and hyperparameters forms a high-dimensional model space. This objective to find an optimal model from this high-dimensional, infinitely large space without any computational guidance is similar to finding a needle in a haystack. Conventionally, machine learning practitioners navigate the model space using data science principles to test various candidate models. Under the hood, Gaggle solves this problem by using Bayesian optimization-based search that looks for regions of the model space where the likelihood of finding better performing models is higher. Next, we show Gaggle's user interface and interactions. Gaggle has the data viewer as the main component that shows the input data as a list view. The other supporting views include the interactive row view, recommendation panel, and the attribute viewer. The data viewer visualizes the data in bins representing class labels. Users can interactively add, remove, or rename class bins, and then drag drop data instances to assign labels to the data items. Users can mouse over any data item to see their feature details in the attribute view on the right. Based on this view, they decide on which class the data items should be assigned to. As users assign class labels by the drag-drop interaction, Gaggle shows other recommended data items in this panel to help speed the process of labeling. The recommendations are based on cosine similarity metric of the interactive data items using their quantitative features. Finally, the interactive row view shows users the set of data they interacted with. It also shows assigned class membership and predicted class membership of the interactive data items to visualize how many of them are correctly predicted by the classifier. Next, we describe how Gaggle operates to ensure navigation of the model space. Gaggle is driven by a Bayesian optimization module that samples multiple classification and ranking models from the model space. We pre-specify a learning algorithm and a set of hyperparameters to construct these models. The Bayesian optimization strategy saves probability distribution of the likelihood of finding better performing models per iteration of model construction. Next, based on metrics inferred from user interactions, Gaggle automatically selects an optimal model and then visualizes the model outputs as users continue to explore the data. The metrics derived from the user interactions are of two kinds: classification metrics and ranking metrics. For classification, Gaggle uses percentage of wrongly predicted interacted data items and a cross-validation score as a metric. The sum total of these are normalized between 0 to 1. For ranking tasks, Gaggle uses three kinds of metrics based on absolute distances from the assigned rank to the predicted rank. I would recommend to read the paper to know further details. To model the classifier, Gaggle uses the interactive data items as a training set, while the rest of the data is used as a test set to validate models. Initially, as users begin to explore the data, the number of data items in the training set are relatively low. Thus, Gaggle augments the training set by finding similar data instances for each class label using cosine distance metric. Next, Gaggle trains a set of classifiers and generates labels for the test data using the trained classifier. Finally, the predicted labels are visualized in the data viewer. Gaggle uses a ranking model technique as described in the work of Zhu et al. To rank data, they create a binary classifier based on a pairwise comparison of a set of data instances that generates a ranking score to each data item. However, we incorporate a custom-designed feature selection mechanism in which Gaggle finds k-best features that makes a data item higher ranked than the other as specified by the user. If users show incoherent interactions that make selection of features impossible, Gaggle uses scikit-learn's k-best feature selection module to find these features. Eventually, Gaggle computes a final ranking score by combining the rank score retrieved from the ranking model and the prediction probabilities of each data items retrieved from the classifier. Conventionally, classifiers are trained on a fixed size training set and then validated on a test set. However, in Gaggle, as users iteratively construct classifiers, the training set grows in size and test set reduces. Gaggle uses this approach to account for user-specified preferences through incremental interactions and to control for model overfitting. Next, we walk you through a demo of Gaggle showing how users can classify and rank data. For the demo, consider the baseball dataset containing 1,300 baseball players and 18 variables such as number of seasons, games played, home runs, strikeouts, etc. The user intends to explore the data to categorize the baseball players. John is a baseball coach and wants to categorize and rank baseball players based on their form. He loads the unlabeled baseball data in Gaggle and starts adding three class labels based on the player's form. With prior knowledge and players' data, he starts to drag-drop players in the respective bins. In the process, Gaggle recommends other players to add to the bins. He verifies some of these recommendations By inspecting their attributes on the attribute viewer on the right, he accepts some recommendations. John sees predicted labels for all the players and thus sees new player assignment to the three classes. He shows new examples as class assignment by drag dropping the players. He spot checks to verify that the models needs further improvement. He verifies new model based on the new examples shown to the system. As Gaggle responds, he pins a few players in the bins, specifying that the labels of these should not change in future iteration. While he agrees with the class assignment of most of the data, to improve it further, he continues showing new examples. He constructs a new classifier and agrees with the labels of the most of the players. Before moving on to ranking the players, he saves the current best classification model. Next, he adds ranking examples to the players by moving players up or down within each class bin. These examples are to record his relative ordering preference of the players. We evaluated Gaggle to seek qualitative feedback from users. We conducted a within subjects controlled lab study with 22 participants. All of the participants were non-experts in machine learning with adequate knowledge of the datasets used in the study. We asked them to perform 4 tasks: multi-class classification and ranking of the data, and binary classification and ranking. We used IMDb Movies dataset and the cities dataset for the study. The order of the tasks and the dataset were randomized to address learning effect. For all the 4 tasks, Gaggle scored highly on user preference rating. However, we noticed that participants found Gaggle to be slightly more precise in modeling binary classification problems in comparison to multi-class classification problems. This can be reasoned by the fact that binary classification is a simpler problem to solve in comparison to multi-class classification problems, especially when users' intent and goals change while they interact with the data. For all participants, we also collected log data such as model hyperparameters to track how models were selected when users interactively navigated the model space. We sought to understand how model hyperparameters switch during the usage. We found that to model the multi-class classification problem, on an average, the hyperparameters switched 9.34 times. In comparison, it only switched the hyperparameters for the binary classifier 5.41 times for all the participants and the datasets. Again, this can be reasoned to the fact that binary classification is a simpler problem and did not need as many hyperparameter switches in comparison to the multi-class problem. Furthermore, we analyzed participant feedback from the semi-structured interviews. We found that they felt Gaggle was easy to use and followed a rather simpler workflow. Specifically, they liked the drag-drop interaction along with the recommended feature that sped up the labeling process. We also expressed how Gaggle can be improved further. For example, a few participants expressed the desire to drag-drop a collection of data instances by using search and filter techniques. A few advanced participants felt the underlying modeling process was unclear to them, which made them wonder what examples they should show to further improve the models. In the process of simplifying the usability of the system, the lack of control of the modeling process appeared to be a trade-off to us. Gaggle's workflow is suitable to model many real-world datasets. For example, using the credit card default payment dataset, a financial analyst may want to classify and rank potential loan applicants. Similarly, using the drug consumption dataset, a narcotics analyst may want to classify and rank respondents to their likelihood of drug use. Thanks for listening. With that, I end my talk, and I'm happy to take further questions or suggestions. I'm currently looking for a job, so please email me for further communication.